Hello everyone. Today I'm going to summarize both paper 9, provenance paper 9 and provenance paper 13. So first I explain both separately, but today I'm going to explain it combined. So first explain paper 9. So in there it's like they have four proposal in this paper. First is formal scientific workflow provenance model, and then provide the security model where the all security specification was handled, like inheritance. It handled consistency, overriding and conflict resolution. And also for the third one, in this paper they explain the security view and secret abstraction view. So if I go through this paper, um, so this is the example, this is the workflow, and this is the corresponding provenance. So when the workflow run, one run of the workflow is one provenance graph we can generate. So this A is one provenance graph. And here, so this is the first one where formal scientific workflow provenance model we generate. And for the next one, we say about the security view. So this is the secure view. So as we can see from the workflow, we can see there was the access control policy. So for the access control, we say okay, these are the negative, means these parameters have no access, like even for the input we can see output, for this output cannot be accessed, this input cannot be accessed. So when we mention that access in our access control policy, and then we can see our what could be our security view for that, and then later on what could be our abstraction view for that one. So this paper has several algorithms for each individual level. So first I'll explain the level 1, which is algorithm 1. In here, first try to specify what is the task level security. So in here, the two things checked is that is it inconsistent, or how can we do inheritance. So for that one, when a parent task, so in this algorithm we can see when the in here we first check the inconsistency. So if we get one task annotation, that is we can say the permission, like access control policy for that one, if is positive but its parent is negative, then there's the inconsistency. But it has no annotation, that means is the root, and is the by default is that positive. And for the next level we can see if there's no annotation, so we try to get the parent's annotation, and that parent's annotation is the child's annotation. So if the parent is positive, it will be positive. If the parent is negative, that task would be negative. So that's our task level. So next one is the port level, which is the algorithm 2. For the port level, the thing is in the for the port we see was the task level annotation for that port. So first we check the inconsistency. So for the inconsistency we need to see the both port has to be the same access. If the access is no, then it should be no for both port. If it's yes, it should be yes for both port. There, if there's yes and no, that means it's inconsistent. So but and for the and if there's no annotation there, so we will inherit the annotation from the task. So in this line 10 you can see T is the task annotation, so that is inherited from the task to the port. So for the data channel, that's little bit more we need to do more explicitly in the data channel, because we have to think uh, different things in here. First we need to get the port annotation, then we need both ports annotation, and if that both port is not the same, that means that's inconsistent. So that's how we can check the inconsistency. And later on, so if we don't know the annotation of the data channel, so what we can do, we can get the ancestor, the task annotation, and check in there. So when we check in there, uh, if data channel annotation is yes but the common task annotation is no, then that's a violation and that's the inconsistency. That's one case. Another case is if data channel say is positive, annotation positive, but the ports are but the port says negative. That should not be the case. If if data channel says no and the both port are yes, that's inconsistency. It implies that if both port is yes, like positive annotation, then data channel should be positive annotation. And here implicitly by this algorithm, it doesn't says that if the both ports are negative, then it doesn't handle that. So it could be both port negative, that data channel could be positive, could be negative. So we can see it in few minutes, like so in the picture, in this picture you can see if both data channel in here is positive, both port is positive, the data channel should be positive. But if both port is negative, uh, then if then that the data channel could be positive or negative both. So and in that way here it implicitly annotate the data channel for that, for the provenance. And when this is negative and the data channel is positive, it creates a dummy data product to handle that situation later on. So there's the third algorithm. And for the fourth algorithm is actually combining the full specification, all specification of task level, port level and data channel level all together, and make it a combined full specification for security. So in this picture we can see this is the full specification SF for the graph, for that workflow, for the provenance. So this handled in this way here. Now let's go to the secure view. So for the secure view, we only do the consume and produce which has the permission, like which has the access over there. So if we go through here, as based on this picture, so as based on this picture, figure 4, we can see there are three cases. So in that three cases we have the produce, which is Q, and also consume, which is P. So how we can make our graph um, for so how can we make our secure view graph, which is here this B1, based on the algorithm. We'll explain that algorithm now. So in this algorithm we can see that for the case 1, if so we make some for security view, we make some empty set of data product, consume and produce, all three set of empty sets, and then we eventually add. If we see that there's a positive, that means it's accessible, then we add that one in that produce or in that consume. So for the case 1 we can see that if that Q belongs in SF, which is full specification of security view, so uh, that is added to the produce, which was empty set, and we then add this one. But when that's the case 2, so as you can see in case 2 in here, when both ports are negative, we have to create a dummy data product. So that is handled in the case 2 in here. So we create a dummy data product DD, and then we include that in produce and consume. But as we know from the case 2 in here, is that just it will access that data channel, but it will not access the actual data product there. So as you can see in this algorithm, so that's just the dummy that will not. So this is how from Q to P, that data channel, if it's positive, that's the case 2 in the picture, how can we handle that? And if that's the case 3, all negative, so nothing will be accessed, so there will be no connection from port to port or port to data channel in there. And I think for this one it handled the only the produce for case 1 in here, so it needs to handle also the consume in here. So that's why the consume is added in here. So that's the security view. um, for the abstraction view, it's explained very nicely in this picture, and then I'll later explain by the algorithm for algorithm 6, is that if we know there is so for if we know in between the task, so for task T1, if we go inside, then we will say it's true, but if not, then it will be false. So from this picture we can see on here T3 would be true, but T4 and T5 we're not going in detail of T4 or T5, so it will be false. So that's how we can see that the total abstraction view of that provenance. So if we go to the algorithm, so that's how they handle. So this is the empty set, like task run, which is the provenance generated. So we only include those ones which has so which are for, we go inside that task, like which is true, and and that's even the parent, even um, so the if the parent is true but the task itself is false, we don't go detail of that one. We'll just go to the task which is true. So that's how we can, and also we can include all the output port and input port and everything in there based on that, and add that as we go forward, and then actually this graph will be generated. Let me show you. This C graph will be generated. So in this paper, what we have we learned that we do our first our specification based on three different levels: task level, port level, data channel level. So all three, we see our consistency, we see the, if there's not no annotation there, we inherit from the parent. So that's for the first part. Then we try to like generate the graph based on our security view. Only those nodes, ports and data channel, those has the positive as a access, we generate a graph there. And also we generate abstraction view for that one, so which is only accessed. Now let's go to different perspective in provenance 13 paper. So in this paper, as you can see, is that they here um, they incorporated the RBAC, role-based access control model, and in here they are doing based on the user role, permission and session. So it's more like based on session. Each session has each user, and that user can have different roles, and then different role has different permission. So let different permission for that particular user. So essentially one user can have different role and different permission. And here this PA, UA and user function and role function is explaining that. So now in this paper they are more into in the 13th paper they're more focused into just inconsistency and inheritance part. But in here there's more equation, we can check more in perspective of a few different things. So in perspective of inconsistency, policy exception, incompleteness, redundancy and irrelevance. So they are checking all of those based on that access policy. So they try to make the policy the best policy, and so there will be no such anomalies in there, and then come up with the transaction. So this in this paper is a little different view from the paper 9. So in here actually they also propose another model. So we know already OPM model and ProfDM model. So they are doing the SIMP model, and they try to collect more like the communication environment. Those are the new relations there. But before we know, even for ProfDM there's actor, data product, process and those things, but there's more relations. But here more uh, more elements or more things are here captured in SIMP. So in here, so for the set, for all the processes, they put in simpy.processes. All the policies they put in simpy.policies. As we can go on, we'll see that they generate the policies first, then based on the transaction, when the transaction happen, so then checking that policy for that transaction, and then uh, validate all the anomalies if it's there or not. So in that regard, we can see, so this is the example table 2. They give an example like for uh, they mention the policies, 15 policies, and they have each user can have probably, or not all the user, but there might be few user can have both roles in a certain period of time, can be manager certain time or worker certain time, then manager, and what's the action, object, and permission for that particular role. So, and here as you can see, this equation is actually straightforward. They are trying to see the consistency. So the action policy, access control policy for I and J, if they're same, then for the role same, the object same, and their action same, but the signs are different, that's inconsistent. So that should not be the case. And policy exception, for policy exception is more like when the transaction is going to happen, like when the actual thing is, they define the policies first, but then when the actual thing is going to happen, to see uh, that it does not have, for the access control policy, the sign is negative, but still that transaction executed, so that's a policy exception. So uh, so as you can see, I can actually show you the later on graph. Yeah, so this is actually the transaction. See what happens. This is the policy tree. So policy tree will handle all different situations um for different policies, but transaction tree is the tree which happens only the transaction is transaction happened. So it will be mostly always subset or same set of the policy tree. So, and also from the equation, I can see how to handle the incompleteness. So when there's no access control policy for a transaction, so that means that's not complete. So that access control, that the policy tree is not complete. And also the redundant, when everything is same, we don't need two policies for that. Policy I and policy J, we don't need two policies when everything is same. For irrelevant, when that is in here, so if there's no processes uh, and no policies there, um, so but put it in the in so there's the access control policy for that, but actually when it's executed, there is no process or no access control in there, not doesn't belong actually in there, but there's something that's actually irrelevant for that. No access requests are issued for to which a given policy is applicable. So that's the irrelevancy. So based on that, if you can go down, we can see the three algorithms. So one is how to analyze policy based, then how to analyze transaction based. Transaction based actually also handle the seeing in the policy one too. And this is the transaction tree. When the transaction happens, uh, we can capture that operation, like the process, all the processes in there is operation data and user, and that user's role also captured in R, and create that tree. And this is the analyzing the policy and transaction. And so when you analyze, we analyze inconsistency, irrelevant, redundant. And for the transaction, it's more like we handle more anomalies like inconsistency, incompleteness, redundancy, and exception handling, policy exceptions. So from this table we can see that which one is handled by those algorithms, which cannot be possible. So now after coming up with these two, I can see if we want to combine both of this one, we can do one thing we can do is that we already know that, so this is more like log based, and in the paper 9 is more like provenance. So we can see from the workflow we can do the capturing provenance, and when after capturing provenance we can say that okay, these things are accessible and these things are not. um, then based on that, what we can do for each run, we can combine it with our ProfDM model, which has all the relations. So we can see for each relation, um, suppose uh, was derived from, actually if there's two or more was derived from, but in between there is not accessible, but still that can be derived, because when we know that this is what the data product 1, the data product 5, but in between there's data product 2, 3, 4. So if we say okay, 2, 3, 4 will not be, cannot be accessed, but 1 and 5 can be accessed, so we can actually from, or not 2, 3, 4, just 1 to 3 data product, and we say data D2 cannot be accessed, but we can access the task, we can access the task T1, we can access the task T2, but in mid in intermediate D2 we cannot access, but we still can generate that, because when you have access D1 and we have access T1, we know for with the D1 the task T1 processed, and after that T1 is processed, what kind of data can be generated, and from that D3 we know this D3 generated as output, and this is the task generated. We can go backtrack and can also generate D2. So we can build something which can handle those situations, and also for the purpose of, also the in we can you can leverage use of the prov model, because prov model also capture the time, so that time could be assessed as a session. I don't know yet how I can formulate the whole thing, but I can see it could be possible based on the prov. They use SIMP, but we can use ProvDM, and actually incorporate all the other anomalies like the redundancy and um, policy exception, irrelevant, incompleteness, all of those in the model, and check that policy first and apply those policies, and in the meanwhile, if try to figure out the cases, the interesting points where the intermediary data product intermediate stuff we can generate even though it's not accessible. So we can find out those cases and find out how to handle those cases. So I think I can go from this point onward and try to figure out the exact cases, how I can make both two paper work together, and finding out more extensive or on top of these two paper what are the other cases we can handle. So maybe next week I'll have a more formulation of those interesting points, and can explain that later. Thank you. Bye bye.